Hi, Lance. I'm also teaching from home. I had to get the backlighting almost a little bit better here. Good to hear from you. There's in your email there was it was going to be too hard to answer without going to video here. So what I'm going to do is I just wanted to kind of show my mug, and then I'm going to X this out. But we do still have. Here's a fun thing. Now here's the video that I picked for this. That I'll send you the link to this too, that your kids might get a kick out of when she shoots the arrow, and she actually shoots 3 arrows here in this video. And I'll send you the link to it, but it's when she shoots it through that's their left. Here's the climax of the scene.
Thank you for your consideration.
You gotta love Jennifer Lawrence. But anyway, I found an old. I haven't used this problem in a while. One of the things that was, not it didn't bother me, but I was like, oh, this is a common mistake that a lot of people make, that they haven't been when they haven't been in physics for a while. In your question, you asked, is the you thought the mass didn't matter for the arrow. It matters greatly, because I think if you're going to shoot a bowling ball, that would go a lot slower than an arrow, right? And I think what you're getting confused with is oh, there we go. That helps. All right, is what you're getting confused with is if I drop something from a certain height, its gravitational potential energy is at a certain height, and if we neglect air resistance, if I drop it from a certain height, it doesn't matter whether it's a bowling ball or a ping pong ball, they're going to hit the ground at the same time, neglecting air resistance. However, what you're doing is you are taking, remember, when you pull that arrow back, and that's what this first problem says. Now this is way beyond the scope of your class, but these first two problems kind of highlight what you're talking about. So Katniss pulls back a bow a distance of 0.51 meters, and I remember spending a lot of time looking up what the forces would be, with a force of 215 newtons, okay, and lets it fly. What is the spring constant of the bow? All right, so that's the first. What you're doing, remember, is you're pulling on something. So you're pulling something. So you're adding your force times distance. So you're doing work. So you're raising. It's like if you raise that bowling ball up before you drop it, you've got to do external work, because it doesn't want to go up by itself because gravity's holding it down. So you got to do external work to raise it up and increase its potential energy, and that's what you're doing here with the bow. So on this first problem, and I'll send you the work on this, is you've got F is equal to kx. Remember that guy? All right, so she pulled on a force of 15. Do I have my calculator handy? Yes, I do. So if you pull on that with a force of 215 newtons is equal to K times 0.51 meters. And your students could handle this kind of stuff. So this is K, and this is how the stiffness of the arrow. So 215 divided by 0.15, we've got about 422. And since we're doing newtons per meter, and that's the force constant of the arrow. Now, when you pull that back, it's got elastic potential energy. So the elastic potential energy is equal to 1/2 kx squared. Remember that bad boy? All right. So, because basically what we're doing is we're taking this Newton force over a distance. So we've got a force Do you see the kx in there? Times the distance. And remember, the force isn't constant. You start pulling, you got to pull harder and harder and harder with a bow. All right, with each time. So 1/2 equals kx squared. So in this one, and that's going to equal 1/2 mv squared of her. That's going to equal 1/2 mv squared of her of the kinetic energy. So this is the elastic potential energy is going to equal the kinetic energy when it flies. All right, I should have turned off my darn email. Hold on a second. It's driving me nuts. Oh, it's not going to let me quit. Oh, that's because I'm talking to you still. Save draft. Yeah, definitely save the draft. I'll come back and talk to you in a minute. I was wondering why the email is still on. But anyway, so you got 1/2 k is equal 1/2 mv squared is equal to the 1/2 kx squared. You know what x is. You know the distance here. We know the mass. I think we're given the mass. I'll look that up. 0.033 kilograms of, depends on your bow. And then so you can calculate the velocity. But look what we have here. If I have a bigger mass, if my mass gets big, what's going to happen to my velocity? It's going to be much lower. I mean, if I had a 3 kilogram bow and just this much energy put into it, because notice there's no mass over here. All right, so this will stay constant. But if I increase the mass, then the velocity's got to go down. All right, so let's just go ahead and finish it anyway. So divide by 1/2 on both sides. So I've got kx squared is equal to mv squared. We know what v is. So kx squared over m, take the square root of the whole thing, will be my final velocity. So what did we get? K was 421 times 0.15 squared, because that's how far she pulled it back, divided by the mass of the 0.033. Now look at that. Now look what we're doing here. We're dividing by a really small number. Really small. So if I'm dividing by a really small mass here, I'm going to have the pretty big velocity. So before I square it, I've got 3,222. Take the 57. So when we do that, we come up with 57.6 meters per second, which your students might be like, well, what does that mean? We'll divide that by 0.447 conversion factor. That's about 128 miles an hour. All right, I'll go ahead. I'll make sure I send a copy of that to you. But that's how that works. Good hearing from you, and that was a great question. And I will finish my email out to you and include these documents in there. All right, out here.